Here at Evergreen Consulting, engineer Shaw Shi oversees plans that will translate Taipei 101's unique exterior into one of the strongest, lightest, and most resilient interiors ever made.
The shape of Taipei 101 is more complicated than regular tall buildings, because simple and straight lines will be easier to work with.
Aesthetically, Taipei 101 is broken into sections resembling a stem of bamboo. But similarities with this fast-growing superplant don't end here. Just like bamboo, the distinct structural sections of 101 strengthen and support the whole building. Each section operates as an independent unit, transferring the building's massive weight away from the outside of the building and into the middle. The result is a stronger, lighter, and more flexible tower. For C.P. Wang, this sort of lateral problem solving has been integral to the success of the project. Their aim is not just to be the highest, but to be their innovative best.
Let me put it this way, it's not like the Wright brothers when they invented the airplane. You know, today a lot of people knows how to build an airplane, but it's how good it is matters.
The design of Taipei 101 requires unique engineering to facilitate a unique shape. But the next challenge facing designers pushes this engineering to the limit. How to make the tallest building in the world stand up against two of the mightiest forces of nature in one of the most hazard-prone cities on Earth. Every year, the people and buildings of Taipei are under attack from two of nature's most primal and unstoppable phenomena.
When you put a tall building on an old secondary earthquake fault line, which runs nearby here, and in a place where you get significant typhoons, that just has major challenges.
The problem is that to resist wind, a building must be stiff. But to survive an earthquake, it must be flexible. Taipei 101 will have to be both.
This is the only super tall building in the world that's designed in a seismically active zone. This is really pushing engineer and construction boundaries right to the limit.
The island of Taiwan sits at the junction of two tectonic faults, where vast plates of the Earth's crust grind together, causing earthquakes. The entire island is unstable. Three smaller faults run directly under Taipei itself, causing hundreds of earthquakes every year. The effect of an earthquake on a giant skyscraper can be catastrophic. The entire building is shaken to its foundation as intense waves of energy from the Earth are transferred to every inch of the building structure. To withstand these shocks, the building needs to be flexible so it can move with a quake and not against it. If it's too stiff or brittle, it can break. Superficial damage like broken windows or walls can be repaired. But any damage to the internal steel framework of a building can be a disaster. As the tallest building in the world, Taipei 101 must be engineered to withstand major earthquakes. But just how major is something of a mystery. Geologist Dunstan Chen is one of the scientists charged with finding out the details.
This is when we make the first design, okay, we have to consider this fault. We know there's a fault somewhere here, but we don't know exactly where it is.
An investigation is launched involving some of Taiwan's leading geologists to find out where the fault is and how far it is from the Taipei 101 site. They need to establish if it's active and how they should deal with it. The results shock everyone.
Then we drill number 4. Okay, we encountered the fault. And this fault actually, the gauge was around 10 meters thick. It's a huge one.
In most earthquakes, the closer the building is to a fault, the worse the impact. The fault found by Dunstan and his colleagues is not only huge, it's close. Only 200 meters away from the 101 construction site. 101 must be prepared to face the most extreme earthquake shocks imaginable. Here at the NECRI facility, scientists use a multi-dimensional shake table to simulate a variety of different earthquake scenarios. Scale models of different structural configurations are tested, and the information gained helps to design buildings that are better able to withstand the devastating impact of earthquakes. An earthquake shock delivers brutal vertical, horizontal, and twisting strain on a building. Every joint of every structural element is strained, and if there is one weak link, the whole lot can go. To keep 101 standing in a major earthquake, engineers develop a complex internal megastructure. The central core of the building is connected to 8 incredibly strong supercolumns by a network of horizontal outrigger trusses. The supercolumns act like a giant flexible spine, enabling the building to flex and move if it needs to, but not break. Although the idea of supercolumns has been used in other buildings before, the size of 101 takes this engineering to an entirely new level. But the threat of earthquakes isn't the only natural force that builders of Taipei 101 have to worry about. Every summer, unstable equatorial air off the coast of Taiwan generates vicious typhoons that lash Taipei. These intense tropical storms, with winds of up to 200 kilometers per hour, can literally blow a building to pieces. But it's not just strong winds that designers of 101 have to worry about. The surface area of a skyscraper is so huge that even a small breeze can still have a major effect. As wind hits a building, it impacts in 2 ways. First, the exposed face of a building can be pushed by the wind like a giant invisible hand. But under certain conditions, the wind can generate pulsing vortexes on opposing sides of the structure. The vortexes begin to oscillate, exerting small but consistent pushes on alternating sides of the building, eventually causing it to sway. Like a child pumping their legs on a swing, each gust of wind adds energy. This swaying can be so severe that occupants of high-rise buildings can experience motion sickness. Normally, engineers can accommodate this problem by making the internal structure of a building stiff and rigid. But being stiff is exactly what designers don't want in the event of an earthquake. Can engineers of 101 design a building that is both stiff and flexible at the same time? For the project to go ahead, they have to.